Hello.
Hi, sir.
Hi. Okay, so we'll wait. Let others also join. Okay. Last class, what we did, Amala? Where were we?
Stability of carbanion free radicals.
Sorry.
Stability of intermediates.
We have discussed hyperconjugation, right?
Yes, sir.
Okay. So I think it's done. Carbonyl intermediate we have discussed, no?
Yes, sir.
Okay. Resonance energy?
No, sir.
Okay. Okay, chalo. Most probably we'll finish this today.
Connecting. Okay, another.
Hello. Yeah, hi Ronnie. How are you?
Hello, sir. I'm good.
Did you watch the video I shared on the group?
Yes, sir.
Finished?
Not the whole video, sir, but I did.
Okay, because the thing is, we are starting, like last class we have done a GOC, but we are starting something else today. Okay, so like whatever you are going to miss, that is there in that video. Okay, so you have to watch that. We are having two different batches right now, right? So that's why I am taking one different topic, which is common for both of you guys. Okay.
Okay.
So those video you must go through. For any doubt, like you can reach out to me anytime, or I'll plan, one another lecture for you guys especially, okay, to cover those topics. But you finish those videos once, okay?
Yes, sir.
Yeah. Okay. It's the screen is visible, right? Okay, guys. So today we are going to start with resonance energy.
Resonance.
All of you guys, mute yourself. Okay. So what is a resonance energy? Write down. It is the resonance, it is the energy difference between the resonance hybrid energy difference between the resonance hybrid and the most stable resonating structures. Resonance hybrid and the most stable resonating structure. Okay. Now you see this example here. If I take the molecule, which is suppose CH3, C double bond O, O minus, and its another resonating structure is CO minus double bond O. This is A and this is B. And its resonance hybrid is this. This is the resonance hybrid. Delta negative, right? Are H of these two structures. This is C. So if you see the energy profile here, the energy profile of these three molecules, this axis is energy and this is the progress we have. Since you see A and B, both are equal contributing resonating structure, right? Both are similar structure. The only thing is we have double bond here and here we have double bond here. They looks like similar structure. So they are what? They are equal contributing structure. So we write here equal RS, resonating structure. Okay. So obviously the energy of A and B will be equal, right? And that will be, suppose the energy is somewhere here we have for A and B. Okay. This is the energy of A and this is the energy of B. We know the real hybrid structure is the most stable structure of all the resonating structure. So energy of this C is lesser than the energy of B, which is suppose we have somewhere here. The energy of C is corresponding to this line we have. Somewhere here, C. So this difference in energy, right, or this energy difference that we have here, this energy difference, we call it as delta E, and this delta E is the resonance energy. Because what is the different definition we have here? It is the energy difference between the resonance hybrid, C is the resonance hybrid, and the most stable resonating structure. So here the stability of A and B both are same, right? So the difference of A and C or B and C will be the resonance energy. Clear? In the question, you don't have to count the resonance energy. You don't have to calculate the resonance energy, but you just have to compare the resonance energy. Okay, calculation is not there, comparison is there. Okay, so how to compare the resonance energy? Heading, you write down order of RE, resonance energy. Okay, the first one is the first. Here also we have 4 or 5 rules actually. Okay, if the compound is aromatic, its RE will be maximum. Then we have non-aromatic, and in the last we have anti-aromatic. Okay, if the compound is aromatic, non-aromatic, and anti-aromatic, its energy will be, resonance energy will be maximum. For example, if you compare the resonance energy of this or the resonance energy of this and the resonance energy of this. Okay, tell me the order of resonance energy. Obviously, the first compound is aromatic, this is non-aromatic, and this is anti-aromatic. Okay, so order of resonance energy is this: aromatic is maximum, then non-aromatic, and then anti-aromatic. Done.
One second, sir.
Let me know once you are done.
Done, sir.
Okay, so this is the first rule: aromaticity, non-aromaticity,
Done,
and
sir.
anti-aromaticity. Okay, second one is, if the given molecules are, write down, if the given molecules are aromatic or non-aromatic or anti-aromatic, means all the molecules are either non-aromatic or anti-aromatic or aromatic, then what happens? Then we say resonance energy, in this case RE, resonance energy, increases with the conjugation. Okay, greater conjugation, more resonance energy. For example, this molecule and this molecule, suppose you have to compare. Okay, or suppose we have this molecule and this molecule. So if you compare the resonance energy, here you see this compound is aromatic in nature, This compound is also aromatic in nature. This compound is non-aromatic, and this one is also non-aromatic. So when both are aromatic or non-aromatic or anti-aromatic, then we'll see the conjugation. You see, this is aromatic, this is aromatic, but here we have more resonating structure possible, and hence the resonance energy will be more for this molecule. Similarly, both are non-aromatic, but here the conjugation is from this carbon till this carbon, but here we have conjugation till this carbon only. So more structure possible here, and hence this one is more stable, more resonance energy. Third one. In case of equal resonance, resonance energy will be more. For example, we have this molecule CH3CO minus, and another one is this CH2 C double bond OH, negative charge. Or we have benzene and pyrrole. Okay, so in these two examples, you see this we have equal resonance. Here we have only resonance, right? So in case of equal resonance, the resonance energy is more. Here also we have equal resonance, and here we have only resonance. So energy in case of equal resonance will be more.
Sir, equal resonance are when all the structures have same contribution, sir.
Same contributing structure, yeah, equal contributors.
Okay, sir.
Next one is cross conjugation and extended conjugation. This means, you see these two examples. Okay. So in the first case, we have cross conjugation. And in the second one, we have extended conjugation. Why it is extended? Because this pi is in resonance with this pi till here. It is in one direction. But here the resonance structure you can draw with this pi bond and this pi bond either in this direction or in this direction. Right. So this is in resonance or this is in resonance. So this pi bond is in resonance with the two other pi bond which are in opposite direction. One is this way and another one is this way, right? This kind of conjugation, we call it as cross conjugation. Cross conjugation decreases the resonance energy. Hence the order is this. Okay.
1 second, sir. Cross conjugation.
Sir,
Yeah.
if the structure is more stable, then it will have more resonance energy.
Correct.
Or the stable. Okay, okay, fine.
What?
Nothing, sir. Got it.
Yeah.
Got it written, sir.
Done?
Yes, sir.
Okay. Next one is overlapping. Means overlapping tendency we are considering here. So if you have 2p 2p overlap, same size of orbital, then the resonance energy is more than 2p 3p 4p and so on. Why? Because as the size difference increases,
Thus, overlap takes place.
extent of overlap,
Reduces.
right? Extent of overlap decreases, right? Which decreases the bond strength. Decreases the bond strength. Okay. For example, see this molecule CH2 double bond CH single bond Cl. CH2 double bond CH single bond Br. Tell me the order of resonance energy. See here what happens. We have 2p orbital of carbon and 3p orbital of chlorine. Yes. So this is 2p 3p overlap and this is 2p 4p overlap. Size difference is more here. Bond strength will be less, right? Hence the resonance energy will be more in this case. Similarly, here you see carbon oxygen. We have 2p 2p overlap, but here we have 2p 3p overlap. So bond strength is more, resonance energy is more. Okay. Electronegativity. In this, if the overlapping is same, if overlapping is same, then we decide on the basis of on the basis of electronegativity. Okay, for example, we have suppose CH3, CH2 double bond, CHOH, and then we have CHNH2. So we have to compare the resonance energy of A and that of B. Now to compare the resonance energy, because the overlapping is same, we have 2p overlap here, we'll draw the resonating structure of this. And the resonating structure will be what? This comes over here, this goes onto this carbon atom. This will be CH2 negative, double bond OH, positive charge on it. And this will be again same, CH2 negative, single bond CH, double bond NH2 positive. Okay. Now this positive charge is more stable on which atom? Nitrogen or oxygen?
Nitrogen.
We know positive charge is more stable on less electronegative element, right? So we can say this B is more stable. This one is less stable. Less stable, and this one is more stable. Hence, this means what? The resonance energy of B is more than to that of A. Try this one.
One sec, sir.
Done?
Yes, sir.
Okay, just a second, guys. Okay, what is the answer here?
Sir, is it BAC in descending order?
BAC. Okay. So when you compare this, here the bonding and here the bonding we have 2p overlap here, carbon and oxygen. And here we have 2p overlap, carbon, nitrogen, but here we have 2p, 3p overlap. So obviously the C is the least here because the overlap is 3p and 2p, so it's minimum. In first and second, we have 2p overlap, so we'll decide on the basis of electronegativity, right? So nitrogen is less electronegative than oxygen, so we'll have here A and then B. Clear? Understood, all of you?
Understood, sir.
Okay, just rules you have to follow. Okay. Now, the last rule we have in this is write down. The last one is the seventh one, which is the Fry's rule. The molecule which has, write down into this, the molecule which has more number of benzenoid form, the molecule which has more number of benzenoid form is more stable and hence the resonance energy is also more. Okay. Compare these two molecules. Which one has more resonance energy?
Sir, B.
Why B?
Sir, because in the first one, two of them are not. One of them is not benzenoid.
Okay.
In B, all of them are.
This is A, this is B. So obviously B resonance energy is more because the number of benzenoid form here is equals to 3. This looks like a benzene. This looks like a benzene. This looks like a benzene. Here we have 1 and 2. Only 2 benzene we have here. So more number of benzenoid form, more stable, more resonance energy. In this too. Tell me second one.
Sir, is it A?
Why A? Yes, why A? Tell me guys, what is the answer? A and B?
A, sir.
Wrong.
Why? Oh,
Because I am saying.
B. I mean, there's only one other choice.
If it is not A, then B.
No, sir, because here it's big conjugation.
No.
No. Okay.
See, actually, whenever you have this kind of structure, so you try to draw the resonating structure of one. If you draw the resonating structure, it converts into this. Right? But here, if you draw the resonating structure, the number of benzenoid forms is always 2. It won't change. Because here we have ring, there we have ring.
Sir,
Yeah.
what if we shift the double like if we make conjugation with respect to here, sir? I'll mark it, then erase it. I can't.
Here you are saying here.
Yeah, correct. Yes, sir. There.
No, that we won't take because it is aromatic compound, right?
Yes, sir.
So the pi electron will be in conjugation in this ring only and in this ring.
So if it's aromatic, it does not want to go outside.
No,
It's
less
conjugated
tendency
ring.
is there. Less tendency is there. You can do that, but the molecule won't do.
Okay.
Got it?
Okay, sir. Yes, sir.
So here we are getting one aromatic structure, right? Benzene structure, and here we have two benzene structure, right? So this one is lesser stable than this. Order is this. This is a method way that we use. Okay. So just keep these rules in mind. This is again, have some water. Yes. So now we have discussed everything in GOC. Okay. Only two more concepts we have to discuss. And then we'll finish this chapter. Okay. Only two more concepts is left. And that is it. Okay. Write down the heading. Comparison of acid base strength. Okay, so Ronnie, Suyog, Yogesh, and I can see Ashwin. Who is this? Ellen, what's your name? and one more random name is there. Okay, so all these guys, you may be, facing some difficulty in understanding these concepts, because few things still you have to understand. Okay, so don't get panic. I have shared the videos with you. You can go through those videos. That's why I was, posting on the group that please go through that videos. Okay, so you finish those videos. I will try to have one more class for you guys only on this topic. Okay, so what you do today, you just try to, sorry, yes, you just try to go through it. I'll explain why all these acid base strength we have. Okay, so second time, yeah, so second time once we discuss this, then you will understand all these things properly. The point is, you may have some difficulty in understanding these concepts. Okay, okay, here is fine, right? But you'll understand it, don't worry. Okay, right. Now to compare acid base strength based on all those concepts which we have discussed so far. Okay, these guys, Ronnie and others, do you know, you have studied the concept of resonance, right?
Yes, sir.
A resonance, right? Aromatic behavior,
Kind of, sir, but
Okay, fine. So in that video, there's a video called aromaticity. Okay, you finish that. Okay, little bit I'll discuss now so that you can understand here. Okay, fine. So acid and base strength, how do we compare? See, general understanding here, it is what? Any compound if you have, okay, suppose we have a compound HA and HB. We have to compare the acidic strength of these two compounds. So we'll write down the conjugate base of this, which is A minus and B minus. Conjugate base of any acid is the ion that you get, negatively charged ion, when you remove H plus from that compound. Okay, like for example, if you have H2O, so the conjugate base of H2O is OH minus. If you have HF, the conjugate base of HF is F minus. If you have suppose H2SO4, the conjugate base is SO4 2 minus, like this. Just you remove H plus, whatever ion you will get, negative charge ion, that will be the conjugate base. Okay. Now the acidic behavior is the tendency to lose H plus ion in aqueous solution. H plus ion in aqueous solution. Okay. More tendency to lose H plus, more the acidity of that compound. Okay. And the more H plus it will lose when its conjugate base, which is A minus for this and B minus for this. If the conjugate base is stable, then the molecule will be acidic in nature. So to understand this, if I write down here, if I'm assuming this, A minus is more stable than B minus, it means HA, the acidity of HA is greater than HB. Since the conjugate base of HA is more stable than the conjugate base of HB. Similarly, we can write if B minus is more stable than A minus, then what happens? HB is HA. So to compare the acidic behavior, we'll compare the strength or stability of their conjugate base. Okay, and you see the conjugate base is a negatively charged ion, right? Now, for example, just we have to see some examples into this, you will understand how to compare the acidity and basicity. First one, you see, if you have these two compounds, double bond here, hydrogen and hydrogen. So we have to compare the acidity of this alpha and beta. Suppose this is beta hydrogen and this is alpha hydrogen. Which hydrogen is more acidic? Alpha or beta, which hydrogen is more acidic? Try this.
Sir, can you go back to the previous slide 1 minute, sir?
Just a second.
So beta.
Beta.
Yes, sir.
Okay. You see here, for this molecule, the conjugate base will be H plus you remove, you'll get this minus when you remove one H plus. And the conjugate base of this is this molecule. This compound is anti-aromatic and this compound is aromatic in nature. This is more stable. We know aromatic compounds are more stable. It means this compound is more acidic. The compound which conjugate base is more stable, that compound is more acidic. Okay? Order will be this. Second one, this two A and B. Compare the acidity.
Beta. B.
Beta is B is more acidic.
Yes, sir.
If you remove H plus, then what we get?
Anti-aromatic, non-aromatic.
This one will get the same thing. This one and this one is, so this is non-aromatic and this is anti-aromatic again. So this is more stable. This one you see? Yeah. A, B and C. Tell me the answer. Okay. See, here we have hyperconjugation plus H effect. Here we have plus I effect. And here we have plus H effect. Plus H effect more dominating, and plus H effect decreases acidity, right? So obviously B is the most acidic one, right? A and C, if you compare, apart from plus H, plus I is also possible here, and plus I is also possible here. But plus I is dominating here since it is closer to this. So B, then C, and then A.
Sir, if you remove the hydrogen from the phenol, from the alcohol, and you have the more stabilizing agent for that, that is more electron donating thingy, won't it be beneficial? Won't it be more stable, more acidic compound?
क्या बोलना चाहते हो?
No, sir. If you remove the hydrogen from OH and CH3 due to plus H plus I effect and all, if it donates electron and more stabilizes it, won't that be the most acidic?
You are removing H plus from which one? A, B, or C?
From OH of all A, B, and C, sir.
So you'll get O negative there.
Yes, sir.
And then we have to see what effect will stabilize that O negative, right?
Yes, sir.
All these plus effect destabilize that.
Plus I will electron donating. Oh,
Yeah, it will destabilize. So plus H will destabilize more than plus A.
yes, sir, got it. I was thinking plus donates, withdraws by mistake. Yes, sir.
Okay, tell me the next one. Done? Okay. NO2, what effect we have?
Minus M, minus I.
Along with minus M, we have minus I also.
I also, yes, sir.
So minus M increases the acidity.
Yes, sir.
So if you compare minus M, minus I dominates here. So this
Yes,
is
sir.
more acidic than this, right?
Yes, sir.
But actually, due to hydrogen bonding here,
Wow.
its acidity is slightly more than this, right? So here we have A more than C, and then we have nitrophenol. Clear?
Yes, sir.
Okay. This compound, you see, We are almost done with this chapter. We'll start the new chapter very soon. What are you doing in the school? The classes are going on, no? Online?
Yes, sir. We are doing alkyl halides and aryl halides. Like
And what
today
about
we
you
just
guys? Chikka. Tell me. Suyog, your classes are going on the school. Ashwin? Online? They are taking online classes.
Yes, sir. The classes are going on.
What they are teaching now?
Sir, reducing of ore to its metal.
What?
Reducing of its ore to metal. Reducing of ore to metal.
So that metallurgy it means.
Yes, sir. Yes, sir. Yes, sir.
Oh my God. They teach all different topics everywhere. Okay. Alkyl halide they have done.
till SN1, SN2 reactions. Today they finished that much.
No, I'm asking these guys. Suyog, Ashwin and all.
No, sir. We just started, sir.
Started. Okay,
Yeah.
fine. This one, acidity order. See, guys, I know you are having this difficulty in plus M, minus M, whatever I'm discussing now. So once you go through the video, you will understand all this. Okay, I'll take one class for that. So don't worry. Just you try to look at all these. What is happening actually? Okay, this one. What is the order we have? What is ABC?
A greater than B greater than C.
Here we have plus H effect. This is plus H and plus H. And plus H is maximum for CH3. Okay. And plus H decreases the acidity. Hence the acidic order is this. Here we have plus H, minus M,
Minus M
plus
and
H. So it is
plus
B is the most, then A,
then C. It's highly destabilizing. C is.
okay. Now, all these examples I have taken, I did not take any ortho substituted benzoic acid, right?
Yes, sir.
Benzoic acid, but not ortho substitute, right? Because we have a different effect here in case of ortho substituted benzoic acid, and this effect we call it as what? Venkat?
Ortho effect. Oh, steric inhibition of resonance effect.
Sir effect, yes. We also call it as ortho effect also. Both are same thing. What is this effect? You write down and it is very important for exam point of view. All these things they won't ask. Definitely it is very important in the other things that we discussed.
Bulky groups attached to the ortho position prevent resonance.
Write down this. What is Sir effect? First of all, you see this SIR stands for steric inhibition of resonance. Guys, mute yourself. I think Venkat, you mute yourself.
Why, sir? What happened? Any disturbance?
I am getting some noise.
Don't know, sir.
Okay. It is steric inhibition of resonance. Means because of steric crowding, the resonance is getting hindered, right? Inhibition of resonance. Resonance affected because of the steric crowding. That is the meaning of SIR or ortho effect. Write down into this the statement you must remember, and once you know the statement, you can solve the question. Okay. But reason also we'll discuss why this statement we have. Write down the statement first. It says what? That ortho substituted benzoic acid is more acidic than para or meta substituted irrespective of the nature of the group. Okay, irrespective of the nature of the group. So what is the statement here? Whenever you have orthobenzoic acid, whatever group is present at ortho position, that does not matter. Okay, orthobenzoic acid is more acidic than meta or para substituted benzoic acid. Okay, in meta and para, we'll decide by those factors like we are deciding here. We'll use that method and we'll decide. But if it is ortho is there, so without any other thing, you should not consider any other thing. Directly you can write orthobenzoic acid is more acidic. Why it happens, you see, suppose you have an ortho substituted benzoic acid. We have CH3 here present. And here we have COOH. So what happens when once it loses this H plus, so it converts into this. Okay. Now this group, because this group is present, so here we have steric hindrance. Steric hindrance. And to minimize the steric hindrance, what happens? The COO minus group that you have, it rotates and changes its plane. So it goes this way actually. One oxygen atom is going into the plane like this, and other two are coming out of the plane like this. It's a thick bond. Okay, so this is going into the plane. It rotates this way actually. This is going into the plane and this is coming out of the plane, right? So it rotates the bond like this because to minimize this steric hindrance, and hence now this molecule is showing equal resonance. It is RCOO minus kind of structure, like CH3CO minus we have discussed, no? Right. So this molecule is not in resonance with this ring now, since it changes its plane But within the molecule COO minus itself, within COO minus itself, the resonance is possible. This resonance is equal resonance, the red one. And this pi bond is not in resonance with this ring. So with the ring, resonance is not possible since it changes its plane. But within this group, COO minus, it shows equal resonance. And hence the conjugate base of this becomes more stable when it is ortho or para substituted. Is it clear?
Yes, sir.
Okay. So if you understood this, fine. Otherwise, you just mug it up. Right? What you have to memorize, orthobenzoic acid is more acidic than para or meta substituted benzoic acid, irrespective of the nature of the group. And this sur effect or ortho effect is only possible for benzoic acid. It is only for orthobenzoic acid. Okay. Any other molecule, it is not possible. Okay. It's very important, guys, for exam point of view. It's very, very, very important. So, understood?
Understood, sir.
Correct. So tell me the acidic order here in this compound. Acidic order A, B, C. What is this ACB niyati? Decreasing or increasing? So here we have SIR or ortho effect plus I plus H. So plus H will decrease the acidity. So A is the most, then B, and then C. Okay. Yeah. So many different examples, questions we have discussed on acidity. One general order I am giving you, just you write it down. Okay. Like this compound RS, general order you write down the heading. It is more acidic than the carboxylic acid, which is RC double bond O OH. And this carboxylic acid is more acidic than phenol, which is this. Phenol is more acidic than water. Water is more acidic than alcohol. Alcohol is more acidic than alkyne, which is RC triple bond CH. Alkyne is more acidic than NH3, is more acidic than alkene. and is more acidic than alkane. This is the overall order. But one exception we have here, this you must remember, they have asked this many times. Generally what happens, water is more acidic than alcohol, right? But in between phenol and water, methanol we have, the acidity of methanol is more than to that of water. Why it is an exception? Because if you compare H2O and CH3OH, its conjugate base is what? And this conjugate base is OCH3 minus. You can see here we have plus I effect of CH3, and here we do not have such effect. So this conjugate base is less stable than this, and hence this one is less acidic than this. But that is not the case. It depends upon the pKa value. pKa value of H2O is observed to be more than the pKa value of CH3OH, and hence Ka value of CH3OH is more, and CH3OH is more acidic than water. So this is just a change we have. In general, what we say that aliphatic alcohols is a weaker base than water, with one exception, and that exception is methanol. Okay. Clear? Done.
Clear, sir.
Okay. One last thing we'll discuss here. The last topic is, write down the heading, SIP. What is SIP?
Steric inhibition of protonation.
Oh, write down in the top, comparison of base. It is a basic comparison we have. Acidity we have done. Comparison of base. Steric inhibition of protonation. Means protonation is difficult here because of hindrance, steric hindrance. Protonation is difficult. What is protonation? Protonation means addition of
H plus.
H plus. Protonation means addition of H plus. So addition of H plus is hindered by the steric crowding. That is steric inhibition of protonation. Now, if you have to compare the basicity of ortho-substituted aniline, write down the statement here. Ortho-substituted aniline are considered as lesser basic than meta or para substituted. Ortho-substituted aniline is considered as lesser basic than meta or para substituted. Right? So basically, if you see the reaction here, aniline is ring, benzene ring, and NH2 present on this ring. This is aniline. Ortho substituted at ortho position, we have suppose CS3. When it reacts with water, it forms NH3 plus CH3 and OH minus concentration. So basicity and nature is what? It is a tendency to lose OH minus ion in the solution, which happens by this reaction. Okay. Now, if this positive charge is stable, it means the reaction goes in forward direction and increases the concentration of OH minus and basicity increases. Okay. But what happens when protonation takes place here onto this nitrogen atom? Here the steric crowding increases between this NH3 plus and CH3. This steric crowding increases, right? And to minimize this steric crowding, the reaction starts going into the backward direction. Right. Change of plane is not possible because nitrogen and hydrogen bonding we have. So change of plane is not possible here. To minimize the crowding, this molecule has less tendency to go under protonation reaction and hence the basicity decreases. Okay. So like SIR, SIP is what? Steric inhibition of protonation, and it decreases the basicity of ortho substituted aniline because of the steric hindrance. Okay. And here also we have irrespective of the nature of the group. Like this example you see. Tell me the basicity order. One more question we'll discuss. Basicity order of this. Done?
No, sir, I was writing theory, so just 2 minutes, sir, please.
Okay, finish it. Okay. What is the answer? Okay, first of all, here we use SIP, right? And SIP we know decreases the basicity. So this will be the third. In this two, here we have plus I plus H. So plus H increases the electron density here. Tendency to donate will be more. So it is 1 and it is 2. Here we have again SIP ortho. What effect we have here? What effect we have here?
SIP.
Here, middle one.
Inductive.
Plus I.
Yes, sir.
And here?
Plus H.
Plus I.
Plus I. We don't have H here.
No alpha carbon.
Right?
Yes, sir.
Plus I increase the electron density. Here the effect will be more. This is obviously 3. This is 1 and this is 2. Got it? Yes. No doubt.
Clear, sir.
Correct. So guys, this is it for GOC, General Organic Chemistry. Okay. We'll start now the next chapter, which is alkyl halide. Fine. Yeah. Okay, guys, like Ashwin, you're there. Ashwin is not there, I guess. Okay, yeah, Ashwin is there. Ashwin, Ronnie, we're going to start a new chapter now, right? So you can, write these notes properly. GOC, whatever is left for you guys, we'll do that later. Okay, we'll schedule one class for that thing. Okay, videos you can see like meanwhile. Okay, so the next chapter we are going to start is alkyl aryl halide. Okay, this is the next chapter we'll start. Just 1 minute, I'll take some water and then we'll start this. Give me 1 minute. Okay. So how do we define alkyl halide, guys?
Alkyl group with halogen group.
What?
Or, sir, as in?
How do we define alkyl halides? Okay, fine. Alkyl halides are what? First of all, you see these two molecules. Alkyl halide is the halogen derivative of hydrocarbon. Aryl halides are what? It is also
Halogen derivatives of benzene ring.
benzene ring, right? So this is aryl halide. One halogen atom attached to the benzene ring. This is aryl halide. Alkyl halide is Rx, where R is the any alkyl group. Okay. For example, you see if I write down one example of it, CS3Cl, the simplest one, methyl chloride, is an alkyl halide. Okay. Some other examples, molecular formula you should know. This kind of structure, CH2 double bond CH, single bond CH2X. So this carbon, double bond carbon adjacent to that, this carbon is the allylic carbon. The position is allylic position, this carbon. Adjacent to the double bonded carbon atom, CH2 double bond C, the adjacent carbon of this is the allylic carbon. Hence, this compound, the general name is allylic halide. Okay. Next one is, if you have benzene ring and CH2Cl attached to it, we call it as benzyl chloride. Okay, benzyl chloride. Like this one is, I said aryl halide, you know this structure. If you have a benzene ring, a ring like this, double bond present here and X here. This is vinyl halide. Vinyl halide. The name is vinyl. You can compare this structure by this one. CH2 double bond C, HX. This position is also vinylic position. Vinylic position. Double bonded
It's a part
carbon.
of the double bond.
Yeah, so double bonded carbon is this vinylic position, halogen attached to this, so vinyl halide. Got it?
1 second, sir. We'll write it down.
Copy down all these. Done? Finished?
Finished, sir.
Okay. Now, the next thing is the preparation method of alkyl halide. We'll first see the alkyl halide and then we'll see in the last aryl halide. Okay. So first method of preparation you write down. Where is the pen? Yeah. So heading right down. Preparation method. Preparation method. There are various methods of preparation of this alkyl halide we have. The first method of preparation is from alkanes. From hydrocarbon you write down. We can prepare this from alkanes as well as alkenes. Okay, so from hydrocarbon, and in this, the first method we'll see from alkanes how do we prepare alkyl halide. Okay, so write down quickly. Write down alkyl halide can be prepared by direct halogenation of alkanes, alkyl halide can be prepared by direct halogenation of alkanes. However, this method is not useful. Since it gives mixture of product.
Sir, is it due to that free radical mechanism thing?
Yes.
Oh,
Okay. In alkane, we have done this chemical reaction of alkanes, right? So
Sir, since it gives what? Mixture of.
it's mixture of products.
Okay.
Okay. Right. So in this, you see what happens. The reaction is the simplest one I am taking. CH4 plus Cl2 in presence of light H nu, it forms CH3Cl, CS3Cl. Okay, but this reaction follows what mechanism? It follows free radical. In hydrocarbon alkane, I have discussed this thing, so I'm not going into all those details. It follows free radical mechanism. So we'll get all possible product here. If Cl2 is in excess, right? If Cl2 is present in excess, then we end up getting CCl4, right on this point here. If halogen is taking in excess, then we'll end up getting carbon tetrachloride, CCl4. So if you have this reaction, I'll write down here, CH4 with Cl2, and excess of this we are taking. So in the first step, H nu, you will get CS3Cl, but the reaction won't stop here. It further reacts with Cl2 because it is present into this. It converts into CH2Cl2. Further, it reacts with Cl2, converts into CHCl3, which further reacts with Cl2, converts into CCl4. The final one is this. This molecule, we call it as chloroform.
so this is that thing used for kidnapping and all, right?
What?
Chloroform is used for kidnapping and all, right?
Yes. Chloroform. Trichloromethyl. Trichloromethane it is, chloroform. Okay. So since you see here, the free radical mechanism is very difficult to stop. We do not have any control in this reaction. So we end up getting CCl4. We get a mixture of product here. Hence, generally this reaction is not useful for the preparation of alkyl halide. Okay. One note you write down. Write down the allylic hydrogen. Allylic hydrogen atoms are much more reactive
So can you repeat?
allylic atoms are much more reactive
Allylic carbon.
hydrogen atom.
Sir, I couldn't hear. Sorry.
I said allylic hydrogen
Okay, sir.
atoms are much more reactive. If I plug in the earphone, am I audible properly?
Yes, sir. Now you are. Now you are.
Okay. So allylic hydrogen is much more reactive than vinylic hydrogen. Okay. This point you must keep in mind. Now, you see this reaction. Suppose we have molecule, say, CH3, this one, right? Br2 in presence of light. You see, this carbon is allylic carbon, yes or no? This one?
Yes, sir.
C double bond C and this C is allylic carbon. So when this bromination takes place, the product we get here is this. This is the product. Allylic position, the reaction takes place. Even if you have reaction like this, any compound we have like this with Cl2H nu. These two positions are allylic position. So anywhere the reaction takes place gives you the product which is this.
So it's like saying halogenation take place at allylic position, sir. Allylic.
Allylic position is there. The hydrogen is highly reactive because allylic radical is stable, no? Resonance stabilized.
Yes, sir.
So allylic position only the reaction takes place. It depends upon the reactivity of hydrogen. So reactivity, I was about to write down this. Let's write down here. Displacement of hydrogen from hydrocarbon. It is maximum for allylic. Then we have 3 degree, 2 degree, 1 degree, and then methane, CH4. Order of halogen and the order it is maximum for chlorine, then chlorine, fluorine, chlorine, bromine, and iodine. Okay, the first three reaction, this three, is exothermic, and this one is endothermic. One note you write down: iodination of alkane
Not possible.
Write down iodination of alkane takes place in presence of a concentrated acid like HNO3 or HiO3 since it oxidizes Hi into I2.
Concentrated acid, sir.
Yes. Since it oxidizes Hi into I2. Okay. So the reaction is endothermic, right? We need to heat this reaction to get the product. Okay, so if you see the reaction here, the alkane RH suppose we have, and this alkane, if it is allowed to react with iodine, it gives, and we heat this, it gives Ri and Hi, right? So this reaction has tendency to go into the backward direction. Forward direction reaction is not possible here under this condition, right? To make this reaction to go into forward direction, we are using an oxidizing agent like HNO3 or HiO3, right? This oxidizes Hi into I2. So further, if you're using iodic acid, HiO3, it reacts with Hi and this converts into iodine plus H2O. Okay, so this, as soon as it forms, it converts into I2. So in the reaction vessel, you are continuously removing this Hi, and hence the reaction is going in forward direction. That's why we are using the oxidizing agent. Understood this?
Yes, sir.
One last thing in this halogenation of alkane, we'll get mixture of product here, and the major product will be according to the stability of intermediate, which is a radical here. Okay, for example, suppose we have reaction like CS3, CH2, CS3. And this reacts with Cl2, H2. How many products possible in this reaction? Could you tell me? How many free radicals we get?
2.
How many different types of free radical we get in this reaction?
Primary and secondary.
We'll get primary or secondary?
And even chloride radical?
Yes, 2 types, primary and secondary. So one radical we get here, another one will get here. So 2 products possible into this, and the products are, we'll have CH3, CHCl, CS3, and the other product is CH3, CH2, CH2Cl. Which one is dominating here? Which one is the major product?
Secondary free radical. So first one, first. Yes, sir, that one.
This one is major and this one is minor, according to the more stable free radical. Okay, so this is important. Another one more reaction we have of alkane, which gives us this thing, alkyl halide. That is this one. When you have alkane RH, and this will also react with sulfuryl chloride SO2Cl2, this converts into RCl plus HCl plus SO2. Okay, in presence of light or HNu. Peroxide also we can use. This molecule, we call it as
Venkat, mute.
Bro, that's not me, bro. That's my grandmom. She's sitting behind me. Sorry.
done. Finish this one. Okay. So hydrocarbon, the first method is from alkane. In this, the second one you write down from alkene. Okay. B. What can we do into this? By addition of HX. Reactivity order is what? HI maximum, then HBr, then HCl, and then HF. This reaction involves carbocation, and hence rearrangement is possible. Remember, we have already discussed this reaction in alkene. Okay. Addition of HBr in presence of light, heat, or peroxide follows AMR. What is AMR?
Anti-Markovnikov.
Anti-Markovnikov rule, right? Only applicable for HBr. Okay. So could you write down the reaction in this, the product in this reaction? This is A and this is B. Both product you tell me. Let me know once you're done. Yeah. So first product is what? Okay. The first product is, we'll get a carbocation here, and the product is CH3, CH2C, CH3, CH2H, and Br. This is A. Markovnikov rule. Okay, this follows Markovnikov rule. Since we are heating it, this follows
Less number of hydrogens.
right? Means the Br minus, the negative part of the reagent, will attach to the carbon, double bonded carbon, which has more number of hydrogen. Okay, so in this case, the answer B is what? It will be CH3, CH2, CH3, CH2Br, and here we have H. So you see here the addition of this thing, H and Br is taking place. Addition of Br and H is taking place to the double bonded carbon atom. When you are heating it, or when you are having some peroxide here, then the addition of HBr follows anti-Markovnikov rule. Anti-Markovnikov means the Br minus attached to the carbon atom, which has more number of hydrogen, and that is how we get this. This is B.
Got it, sir.
Any doubt?
No, sir, all clear.
Okay. Next method, write down from alcohol. Are you getting it, Ashwin? Ashwin, Ronnie, Suyog, are you getting it, all of you?
Yes, sir.
Okay. So these are the two methods of preparation. Next one, write down the second method of preparation is from alcohol. From alcohol. What do we do in alcohol? Write down into this.
So alcoholic KOH and then probably halogenate. Can we do that?
Yeah, just 2-3 points to write down first.
Yes, sir. One second.
Alcohols are considered to be the best starting materials for the preparation of alkyl halide. Okay, best starting materials for the preparation of alkyl halide. In this reaction, alcohols are allowed to react with
Sir, should it be chloride or halide also is fine, sir?
Sorry?
Should it be only chloride or halides are also fine? Alkyl chloride, alkyl halide.
I have given the general term alkyl halide. So you can prepare chloride, you can prepare bromide, iodide, anything.
Okay, sir. Okay.
Okay?
Yes,
Alkyl
sir.
halide it is.
Okay, sir.
Write down in this reaction, the alcohol is allowed to react with HX or PX3 or SOCl2. HX or PX3 or SOCl2 to give RX, that is alkyl halide. Right? So overall, the reaction goes like this. We have an alcohol, say ROH, and this ROH is allowed to react with HX or PX3 or SOCl2, SOX2. So you'll get RX here generally. This is the compound we get. Okay. The order of, if you see this HX, so order of hydrogen halide is this. HI is most reactive, HBr, and then HCl. HF, the reactivity is very small, it does not react with alcohol. Okay. Tertiary alcohols are also very highly reactive into this because it forms a stable carbocation. So this reaction also involves the formation of carbocation. Okay. If you have 3-degree alcohol, the mechanism is SN1. If you have 1-degree alcohol, the mechanism is SN2. And if you have secondary alcohol, it can be both, either SN1 or SN2 depending upon the condition. Both reactions are equally favorable, right? It depends upon temperature and other conditions. But 1 and 3 will have SN2 and SN1 respectively. Okay. Suppose we have this alcohol CH3CH2OH reacts with HCl in presence of anhydrous ZnCl2. It gives CH3CH2Cl plus H2O. This is the product we get. This reaction we call it as Groove's method. GROOVES. Sorry.
Sir, I didn't understand SN1, SN2 properly, sir.
Don't understand. We'll discuss today. Wait.
Okay, sir.
Okay. Just to try to understand one thing. In S1 reaction, it is a 2-step reaction, forms carbocation. SN2, 1-step reaction, carbocation does not form. I'll share video for this, okay?
Yes, sir. Why is it called SN2 if it takes only one step? I mean,
Because
what-
SN2 stands for second order nucleophilic substitution reaction.
Oh, okay, sir.
SN1 is first order nucleophilic substitution reaction.
Okay, sir.
Okay. So there are many things to understand into this. Okay.
Yes, sir.
I'll share the video for that. You just go through that.
Okay, sir. Okay.
Okay. But those who want to understand things in depth, I will share video for that. Okay. But basically, if you have this information that SN1 is a two-step reaction, it involves formation of carbocation, right? So in this we have carbocation forms and hence rearrangement possible. In SN2, carbocation does not form. It is a one-step reaction. This 2-3 information, if you have for both reaction, it is enough for you to do questions like board exams and others, right? But if you want to get the things in depth, get the concept in depth, I'll share video for that. Okay, for SN1 and SN2.
Okay, sir. That'll be helpful, sir.
Okay. That's the thing here. So HCl with anhydrous ZnCl2, it involves this thing. The process here we call it as Groove's method. Okay, and it forms alkyl chloride. Okay. Could you write down the product in this reaction? HCl. Write down the product in this reaction. Are you done?
Done, sir.
Yeah, yes, sir. Done.
Okay. So what is the product we get?
Sir, is it 2-chloro 3,3 dimethyl butane?
It's wrong. See what happens in the first step. H plus protonates this oxygen, right? So it forms CH3, CCH3, which goes out and gives the carbocation here. Then next what happens? Methyl shift gives you tertiary carbocation. Positive charge here. And then the Cl minus get attached onto this carbon atom. So it will be CH3, CCH3, Cl, CHCH3, CH3. This is the answer for this question. Understood? However, it is a tertiary secondary alcohol. So here we are assuming SN1 reaction actually. Is it clear?
One more question, sir, please. Yes, sir, it's clear.
Okay. So in this only, the other reaction we have C2H5OH alcohol combines with PCl3 and forms C2H5Cl. The reaction is not balanced. That is not required. I'm just writing down the product here. H3PO3. Okay. CH3 CH2OH plus PCl5 forms again C2H5Cl plus we'll get POCl3 plus HCl. This is the reaction we have. And the last reaction is
So how do we predict the products?
what?
How exactly do we predict the products?
One thing is very common here. Whenever we use PCl3, you'll get H3PO3 out.
Okay, sir.
For PCl5, you'll get POCl3.
Always.
It is. You'll see the reaction of this. Pentachloride, you'll get POCl3 out and HCl. This POCl3 forms in PCl5 that you can memorize.
Okay, sir.
HCl also will get in vapor form here. This reaction takes place in pyridine solvent, and the name of this reaction is Darjan's method. Done?
Sir, 2 minutes, sir, writing.
Okay. Tell me, guys, finish.
Done, sir.
Okay. Now you see the another method of preparation is by halide exchange method. Two types of reaction we have in this. One is Finkelstein reaction. In this reaction, what happens? You have an alkyl halide Rx. It reacts with NaI in acetone. The solvent we are using is acetone here. It forms Ri plus NaX. Reversible reaction. So this X can be Cl or Br here. Okay, this reaction is Finkelstein reaction. By this reaction, we cannot obtain alkyl fluoride. Okay, what happens here? Why I will take this? See, the solubility of sodium halide in acetone is this. NaI is most soluble. Then we have NaBr, NaCl. This is the solubility of Na halide, sodium halide in acetone. Right? So what happens, since this NaCl and NaBr that forms here, right, is less soluble in acetone, and we can precipitate it out easily, right? That's why the reaction has tendency to go into forward direction, right? The reason is NaCl and NaBr is less soluble, right? That's why we are using this method for the preparation of what? Alkyl.
Alkyl halide.
Alkyl.
So what about, sorry.
Okay. Now, for what happens for alkyl fluoride?
Yes, sir, I was going to ask that. NaF, for example.
For alkyl fluoride, the reaction we use, that the name is Schwartz reaction. And for this reaction, we use any fluorinating agent which provides F minus. For example, Hg2F2 we can use. Mercurous fluoride, we can use SbF3. Antimony trifluoride, we can also use AgF, silver fluoride, for this purpose. So suppose we have two molecules of CS3Cl, and this combines with mercurous fluoride, that is Hg2F2. This converts into 2CH3F plus Hg2Cl. This we use for this thing, preparation of alkyl fluoride. Why we do not use RF here? Because the bond is very strong here. That's why it's difficult to break this bond and replace this I over here. That's why this method is not useful for the reaction of RF with this. Correct? Yes.
Understood,
Okay,
sir.
we have two more preparation method. We'll finish these two and then
So
we'll
just
take
a second. Can you go back, please?
No.
Yeah, sir. 1 minute.
That's Schwartz reaction. Thanks, sir. Done, sir.
Done?
I'm done. Yes, sir.
Okay.
Pro tell if you are done also.
Yes, sir. Done.
Yeah. So last two preparation method we have. Write down the next reaction is Hunts-Dicker reaction. It's very simple reaction. We use the salt of silver here. Like for example, 1 point first you write down, it follows free radical mechanism first of all. Mechanism. The reaction is RC double bond OOAG, silver salt we are using. React with H2X2. It forms RC double bond OOX and AGX it forms. Okay. Further, when you heat this or in presence of peroxide, it converts into R, C double bond O radical and X radical forms. This radical further convert into new radical and CO2 goes out. Okay. Now this radical and this radical combines together and forms the compound which is RX here. Okay. So overall, if I write down the reaction, suppose the reaction is CH3, C double bond OOAG combines with Br2, it forms, see the alkyl halide that we are getting this with respect to the R group of this salt, right? RX. So what we get here, R, Br, CS3Br plus CO2 plus AgBr. Did you understand this? Yes or no?
Yes, sir.
The first point you write down here, we get alkyl halide. We get alkyl halide with respect to the alkyl group of silver salt.
So what exactly does that mean, sir?
We are getting RX, no?
Yeah.
R is the alkyl group of that salt, RCOH.
Oh, okay. Got it, sir.
RX, right?
Sir, can you repeat the statement?
We get alkyl halide RX with respect to the alkyl group of the silver salt. Okay.
Yeah, yes, sir.
Write on next line. CO2 molecules eliminate in this reaction. CO2 molecules eliminate in this reaction, hence reduces the carbon chain, by one carbon in the product. Okay. Okay. Another thing, from this reaction we can prepare alkyl and aryl halide also. This R can be alkyl or it can be benzene ring also. Aryl also it's possible. So it gives both product, alkyl halide and aryl halide. Free radical mechanism, it is already given, right? It follows free radical mechanism. Done?
One sec, sir. I'm writing theory also. Just a minute, sir. Got it, sir. Done.
One exception we have here, write down iodine under such condition gives ester as the final product. So this X can be either Cl2 or Br2. Iodine under such conditions gives ester as the final product. Reaction is this. This is the reaction we have for iodine.
The fluorine.
The last preparation method, it is reaction with NBS. We also call it as allylic bromination. This NBS stands for N-bromosuccinamide.
Sir, in Hunziker reaction, what happens to fluorine?
Fluorine.
Yes, sir.
See, fluorine reaction usually we do not carry out, okay, because of its small size and high electronegativity. Right?
Okay,
so,
sir.
You see, in most of the reaction, not only for Hunziker, most of the reaction, those reactions are true for chlorine and bromine only.
Yes, sir.
So that's the thing. It's small size and high, bond strength. Under normal condition, the reaction of fluorine is not taking place.
Okay, sir.
See, allylic, it is the allylic bromination. Means what? At allylic position, bromination takes place. Means bromine attached at allylic position. Write down. This means allylic substitution means the substitution of bromine atoms takes place of bromine atom takes place at alpha carbon with respect to the carbon-carbon double bond. Okay. There's no mechanism here in this reaction, just you have to understand that how the reaction you have to write. Okay, N-bromosuccinamide is this compound. CH2 C double bond O, C double bond O. Here we have nitrogen and here we have Br. So N-bromosuccinamide is this. This compound is N-bromosuccinamide. Okay. Now when the reaction takes place of this CH3CH double bond CH2 with NBS, like this only you'll get, in presence of CCl4, inert solvent, H nu, light. So substitution of bromine takes place at alpha allylic carbon. It is allylic bromination, right? So this bromine comes over here and this hydrogen attached onto this nitrogen. So the product here is CH2CH double bond CH2 Br plus, here we'll get nitrogen. This is the product we get. Allylic substitution. So the bromination takes place at benzylic position. Oh, wait, write down like this. I'll give you this thing with reaction.
Benzylic, sir.
Wait, I'll tell you how it happens. Yeah, benzylic also possible. I'll show you in the reaction form.
Okay, sir.
See, one note you write down first here. Notice when double and triple bond are present in the same molecule, when double and triple bond are present in the same molecule, then the preference is given to the alpha position of triple bond. The alpha position of triple bond. Okay. Now you see just two reaction here. For this one, if you have, suppose this molecule CH3, CH double bond CH, single bond C, triple bond C, CH3. And the reaction of this with NBS, with all those reagent that we have, CCl4 and H nu. So you see here, this is the alpha position of triple bond, right? And the alpha position of double bond is this. So when both are present, then we'll give preference to the triple bond, alpha position of triple bond. So the product here is what? H3C, CH double bond CH, single bond C, triple bond C, CH2, Br. Okay, this is one reaction. The another example, if you have toluene, okay, CS3 present here. Reaction of this with NBS with CCl4 and we heat this H nu. So this bromine comes over here, benzylic position, because that is the only possible position we have. It forms CH2Br. One hydrogen comes out from this, P of bromine attached. Because with respect to this double bond, you see it is the allylic position. And the last one is this. Tell me the answer in this reaction. The product is what? At alpha position. So here bromine will get attached.
Up or down, sir? Anywhere.
Up or
Same
down,
thing.
same thing. ठीक है?
Understood, sir.
Okay. So this is it for the preparation of alkyl halide. Okay. We'll take a break now. We'll resume the session at 6:50. Okay, 6:50. I have some about 6:50. We'll resume. Okay, and then we'll start the properties of alkyl halide. Okay. Once we finish alkyl halide, we'll start with aryl halide then. Okay. Aryl halide is not that big. Few reactions we have to see, and that is it. Okay, guys.
Okay, sir. Okay, sir.
Take a break. Don't leave the session. Let it be as it is. Okay, we'll resume the session at 6:50. Yeah.
Yes, sir. Yes, sir.
Hello? Sir?
Shut up.
Why?
Sir, will be back by what? 6:50, didn't
Simply.
he?
Huh?
Simply.
Okay.
Hello.
Yes, sir, back.
Yeah. Okay. So preparation is done, right?
Yes, sir.
Write down next the property of alkyl halide. Okay. The first thing is dipole moment. Okay, the important one I am discussing here. If you talk about dipole moment, we know it's a vector quantity given by mu is equals to q cross d, right? And the direction is what? From positive to negative. Positive charge to negative charge is the dipole moment. Okay, so the dipole moment of alkyl halide. Okay, why this dipole moment is there in the molecule? Because carbon, if you see, carbon and halogen
Electronegativity
bond,
difference.
right? What?
Electronegativity difference.
Yes, it is because of the minus I effect here. Minus I effect of halogen. Okay, it drags the bond pair of electron towards the side, delta negative, delta positive. So this charge separation creates a dipole here. And hence we have a dipole moment, correct? So if you compare the dipole moment of CH3F, CH3Cl, CH3Br, and CH3I. Okay. See, dipole moment, it depends upon two factors. One is what? One is charge. If charge increases, dipole moment increases. And other one is distance between the charge. Right? Distance between the charge. This distance is d, which is nothing but the bond length, correct? Yes or no? So bond length and charge is a factor here we have. Okay. Now, what should be the dipole moment of these four molecules? CH3Br. By mistake, I have written this. This is CH3Br. Tell me the order of dipole moment here for these four molecules.
Sir, F greater than Cl greater than Br greater than I.
F greater than
Cl greater than Br greater
Cl
than
greater
I.
than Br greater than I. Okay. So why F has maximum dipole moment?
Sir, it's the most electronegative. As we go down the group, electronegativity decreases. So we can have somewhat similar electronegativity of
So
iodine with respect to carbon.
electronegativity more, charge will be more. But what about D?
Oh.
D will be the least, no?
Yeah.
Distance here, fluorine size is the smallest one here. So carbon,
Yes, sir.
fluorine,
So-
D is minimum. Carbon, iodine, D is maximum.
Maximum,
But
yes, sir.
iodine electronegativity is minimum. So charge here is minimum, but charge here it is maximum, right? So we have two contradictory factor here, and hence the dipole moment becomes what? Experimental.
Yeah, experimental.
Observed dipole moment here is, it is maximum for CS3Cl. Then we have CS3F. Then we have bromine. And then we have iodine. So we can say in case of chlorine, the distance D dominates here. And that's why the dipole moment of CS3Cl is maximum out of the 4. The same question they have asked once in the exam. Keep this in mind.
Sir, in electrostatics, we learned that dipole moment is from negative to positive. Why is this difference happening,
in
sir?
physics, it is ulta.
Oh, why? Normal convention.
It is a convention, but there is a reason, not that important. I don't remember right now. Okay, but it's just a convention. We take this like in one simple example. You see, pressure in chemistry, we consider suppose we have gaseous system, right? So in chemistry, we consider the internal pressure, like the pressure of gas onto the wall. But in physics, we consider the external pressure, atmospheric pressure. Okay,
so
both are
that's pretty much the same, like just opposite in sign, right? If it's kind of
just
reversible
opposite
and
in
stuff.
sign, yeah. So convention is this. Similarly, here the convention is that the dipole will take from positive to negative. That's how the thing is.
Okay, sir.
Okay, so no, like there's no this thing of explanation here. Convention, we can say. Okay. Now you.
So one second. Can you go back, please? I was writing theory now. And sir, is this dipole order true for all alkyl halides?
What?
Is this dipole order ClFBrIa true for all alkyl halides?
Yes. It's true.
Okay, sir. Done, sir.
Done.
Yes, sir.
Okay. Now another relation we have, that dipole moment that we observe here, observe. For the molecule like this, if you have only one Br attached to it, one halogen atom, it is maximum. As the number of halogen atom is increasing, dipole moment is decreasing. And the last we have, where the dipole moment cancels out, CBr. Could you tell me the comparison of dipole moment here?
Sir, CBr4 dipole moment is like 0, right?
What?
CBr4, this guy, dipole moment is almost 0, right?
Just a second. What? Tell me.
CBr4.
Dipole moment is 0.
Okay, sir.
See, dipole moment is the vector quantity, no? So we'll calculate by the law of vector. Actually, you see, when you draw the structure of CH3Br, CH3Br is something like this, tetrahedral structure.
Yeah. CH4 is tetrahedral, so yeah.
So carbon hydrogen bond, we do not have any electronegative difference, right? So we have dipole moment like this. in upward direction like this. There
Yes,
is no
sir.
cancel, like that. This dipole moment is not getting cancelled, right? Because there's no net dipole moment this side. But when
Yes,
you
sir.
draw other structure like this, CBr, BR, H, and F. So here you see the dipole moment we have in this direction and in this direction, right? So net
Yes,
dipole
sir.
moment will be what?
Will be somewhat
Will be
upwards. Yeah.
mu net, right?
Yes, sir.
But this value will be lesser than this value because the bond angle is what?
109 degree.
109, right? So it is
28
obtuse
minutes.
109.
Oh, yes, sir. Yes, sir.
Right? So obtuse, so cos theta will be less than 1, right? Sorry, less than 0.
Less than 0. Yeah.
Hence the mu net will be, when you calculate this, the net dipole moment will come lesser than this value. That's why we have this order.
Oh, okay, sir. And also a bit
Okay.
of dipole moment in the vertical direction gets cancelled. So,
Yes, that's why it is maximum.
okay, sir. Got it.
If you have one more BR here, right? So these two will have a resultant in this direction. Then this one and this one will have a resultant in this direction. That will also even lesser than this because in this direction cancel out this.
Oh, yes, sir. Sir, but then if you have CH3Br in place of one hydrogen, the bottom or middle hydrogen here in the second one.
No,
in
carbon
case we
hydrogen bond, there is no electronegative difference. So no
yes,
charge
I
separation.
understood that. No, what, sir? See, directly below there's a hydrogen, right?
Just a second. Yes.
Yes, sir. So in that hydrogen, if we replace that with Br, so the up Br, down Br, 100% gets cancelled, and there's only one Br left. So won't that be equal to the first Br?
It's not linear, da.
Oh yeah. Okay, got it.
Linear, right?
Yes, sir.
Correct. Understood.
Got it, sir. Got it properly.
Okay. So this is the order we have important, must keep in mind. Okay. Now next property you write down. In isomeric alkyl halide, isomeric RX, the boiling point is maximum for primary, then secondary, and then tertiary. So as branching increases, boiling point decreases. Okay, this is for primary, secondary, and tertiary. Okay, if you have different halide group, then we have maximum boiling point for iodide, then bromide, then chloride, and then iodide, then fluoride. Maximum boiling is. Okay.
And sir, for the second one, the benzyl bromide thing, is the first one has more dipole moment?
Oh, I did not discuss this one. Yeah, I forgot. Sorry. Yes, which one has more dipole moment? Obviously, this is delta negative. This is delta positive. Delta negative.
Yes, sir.
You see, first of all, this carbon is sp2 here, right? And this carbon is sp3. So first of all, the electronegativity of this carbon is more. So charge separation is not that great, right?
Yes, sir.
So charge separation is not that great. Secondly, because of plus sign nature of this, the bond length is also lesser than this because it has partial double bond characteristics. What?
Got it, sir.
Right. So bond length is less here, D is less, charge is also less. So obviously the first one has more dipole moment. Okay. Now you see the chemical reaction that these alkyl halides shows, it is because of the charge separation only. Okay. the carbon halogen bond has charge separation, delta positive and delta negative. That's why it mainly shows two types of reaction. First one is substitution of nucleophile, that is nucleophilic substitution reaction, and the second one is elimination reaction. Okay, which mainly forms alkene, right? Another type of reaction we have this thing, reduction reaction, Franklin reaction, Corey-House synthesis. All these reactions we have discussed already, right? So first we'll see the reactions of this alkyl halide, and that is mainly substitution, nucleophilic substitution reaction.
So what's
Right now-
Corey-House synthesis? What's Corey-House?
Corey-House synthesis, I have done this in alkane chapter. एक बार notes खोल के revise करो.
Yes, sir. Okay.
Preparation of alkane.
Yes, I'm checking now. One second.
Don't check, first you copied on this.
Okay.
Okay. See, like I told you that I will share the videos of reaction mechanism where we have discussed in detail what is SN1 and SN2 mechanism, but little bit I'll just explain here to make you understand the concept. Nucleophilic substitution reaction it has 8-9 types of nucleophilic substitution reaction total, but we'll see only 2 for now, right? And these 2 are the only important one. We have other types also, but important one is SN1 and SN2. We have SN1 prime, SN2 prime, SNAE, SNEA, SNNGP, SNI. There are many different types of reaction. Okay, but we are discussing only 2 as of now, right? This SN1 stands for first order nucleophilic substitution reaction. Okay, substitution reaction. This is what? Second order nucleophilic substitution reaction. Don't ask me order now, because I have to then discuss many things to make you understand. Okay, order we'll discuss in chemical kinetics.
I was going to ask that, sir, but okay.
What?
I was going to ask that.
That's why I told it.
Yes, sir.
Okay, now SN1, the basic difference in these 2 reactions is what, which you have to keep in mind and important. SN1 is a 2-step reaction. It's a 2-step reaction, and this is single-step reaction. I'll show you one, example also, single-step reaction. Second thing, the first step here, the first step is the formation of carbocation in this. So first carbocation forms, and in the second step what happens? Nucleophile, that is Nu minus, attacks on the carbocation. So now when carbocation forms, so we can have a rearrangement possible, right, for the carbocation to get more stable carbocation, correct? What?
Yes, sir. Methyl shift and all.
Yeah. So SN1 reaction is what? Is something like this: Rx plus Nu minus. It gives RNU and X minus. Right. Even SN2 reaction is also, if I write, that is also the same thing. Rx plus Nu minus gives RNU plus X minus. So we'll get the same product, but the path of the reaction is different here. In this reaction, what happens? SN1, in the first step, this Rx, this X is a good leaving group. Halide ions are good leaving group. And leaving groups are good base also, right? So it's a good leaving group. It goes out and forms a carbocation R plus and X minus. Right, so this is the carbocation forms in the first step, right? And in second step, this carbocation, which is the most stable one, gets attacked by the nucleophile and forms R and U. The first step of the reaction is the RDS, rate determining step, slowest step of the reaction. Okay, this is how the reaction proceeds. SN1. SN2 is, we'll have this only, it's a one-step reaction, but we'll have here a transition state in between. And that transition state is the R and X. The X ion, this leaving group, is about to leave, the bond is about to break here. And this nucleophile, the bond is about to form, Nu. So this is a transition state we have here. Okay, transition state we get here. It's a TBP, trigonal bipyramidal structure we get here, right? And eventually what happens, this bond breaks and this bond forms, we'll get this one. It's highly unstable, right? Even temperature, like the kind of solvent we use for this reaction, that also have a role here, whether the reaction proceeds with SN1 or SN2. Okay, the nucleophile that we are using, that also have a role here, that the what path of the reaction is. Okay, both are competitive reaction. In any reaction, if I say that the major product is this through SN1, it means what? It does not mean that SN2 is not taking place. It means the minor product we are getting from SN2 reaction also. So both reactions are competitive. In any reaction, both mechanisms are competing with each other, right? The one which the factor or the condition of the reaction, whatever we have, that will favor one particular type of mechanism, either SN1 or SN2. So the favored mechanism gives you the major product in the reaction. Understood?
Sir,
Ah.
sir, if both the reaction give same product, like how do we know which product has come from which reaction, sir?
That's what I'm telling you. We have SN1 is carbocation formation, right?
Yeah.
And SN2 there is no carbocation. So what we can conclude, I am not talking about the solvent factor. For that you have to see the video. Okay, there are many things to talk. Okay, so you have to watch if you want to go into detail of this. Okay, but basic understanding, how do you have that? I'm trying to make you understand. Since carbocation forms SN1, right? So whenever we have 3-degree carbocation or stable carbocation, say benzyl, allyl, if at these positions halogens are attached, then they have tendency to go via SN1 mechanism because they forms a stable carbocation. Mute yourself, Venkat.
Okay, sir.
Okay, so if the halogen atoms are attached to the carbon atom, which can probably give the stable carbocation, then the mechanism is SN1. Like 3 degrees is stable. So 3-degree halide mostly go by SN1 mechanism, right? So this is the order we have for SN1. SN2, the order will be reversed. Okay, for SN2, if you have if you have methyl group, then it is maximum, then 1 degree, then 2 degree, then 3 degree, then we have allyl, and in the last we have benzyl.
Sir, vinyl?
Vinyl is not that stable. Carbocation is not stable.
Okay, sir.
Okay. So basically, one thing you can understand, wherever you get stable carbocation, okay, so stable carbocation ke, in that case the mechanism will be SN1 favored, because the carbocation is stable, so that will form in the reaction, right? If a carbocation is not
Yes.
stable, so that won't form in the reaction, because the major thing is that. Okay, then you can ask me, so what happens with 2 degree? Right, what happens
Yeah.
with alkyl halide? Correct. So 2 degree alkyl halide, actually it favors both SN1 and SN2. So
Yes,
to
sir, you
determine,
just told that here.
yeah, whether it is SN1 and SN2, you have to consider what solvent you are using and what kind of nucleophile we have, whether it is weak nucleophile or a strong nucleophile. All those factors you have to consider. Based on this, we can have either SN1 or SN2. So for this part, I will share the video with you. Okay, but basic
Okay, sir.
understanding is this. 3 degree stable carbocation favors SN1, 1 degree unstable carbocation favors SN2. Okay, now the reaction, how it
Sir,
goes.
sir.
What?
So 1 second, can you go back, sir? Thank you, sir. Just a minute. Slowest. Done, sir.
Okay, now we look at the reaction here. So first we'll see halogen derivative, which shows SN2 mechanism. However, we know under what condition SN2 mechanism is favored, right? So that condition will be true, like 1 degree or methyl, okay? But what all reactions we have which favors SN2 mechanism? The first reaction you see here, suppose we have RCN, sorry, Cl, it's alkyl halide now. So RCl, and it reacts with, suppose, NaCN or KCl, any one of these two. Mechanism is SN2. The product we get here is RCN, and Cl minus goes out as a leaving group. Okay. Second reaction in this, if you have RCl and this reacts with AgCN, what is the product we get?
Isonitrile?
Yes. Now, why this happens? Why we have CN there and NC here? अरे समझ में आ रही है बात?
Yes, sir. Your baat, you got it, but answer don't know, sir.
Okay. See, the reason of this is these compounds are ionic compound actually. So NaCN or KCN, ये कैसा होगा? It will be like this: Na plus and Cn minus, or K plus and Cn minus. ठीक है? अब this Cn minus you है, it is ambidentate ligand actually. अब again this term you do not know, so I'll explain this.
May or may not accept protons. Like it's an ambident. Both character is there. I know this.
It's ambidentate ligand like this. ऐसा है. ठीक है? So, and it behaves as a nucleophile also. Nucleophiles are what? nucleophiles are electron-rich species, or the molecule which has lone pair on it. For example, H2O. H2O also behaves as a nucleophile. Okay? So since carbon has lone pair of electron, nitrogen has lone pair of electron, so both has tendency to attack onto this alkyl group. Why it will attack over here? Because of this electronegativity difference, it is delta positive and this is delta negative. So we have this positive negative and these molecules dissociates as this. So we have two sites of attack. One is carbon, other one is nitrogen, right? Both side attack is possible. Means carbon can also attack onto this alkyl group. Nitrogen can also attack onto this alkyl group, right? The one which has the more tendency to attack gives you the major product, right? So which side will attack? Obviously carbon, because carbon is less electronegative, can donate its electron to the positive charge alkyl group.
Oh, yes, sir.
What? What about others? What are you doing, guys? You're not even, you're sleeping or what? Guys, please type
Understood, sir.
CLR. CLR, please type if you understood this. Quickly. Yeah. Okay. So we have Cn minus and both side attack is possible. That's why we get RCN, and in few amounts or in lesser amount, we'll get RNC also here as the minor product. Because nitrogen, however, has less tendency to attack, but we cannot eliminate the possibility of formation of this, correct? So this will be minor here. Major is RCN cyanide, because carbon being less electronegative can easily attack onto this alkyl group. ठीक है बात? Clear?
So just a second, sir. I'll write that ionic thing explanation and all.
Let me explain this first, then you can write. I'll give you time.
Okay, sir.
Now in AgCN, what happens? The major difference is this was ionic. AgCN is covalent in nature. So covalent means what? This bond is there. It won't exist in the form of what? In the form of ion, right? Si. So what happens? This site is not available. It is bonded with silver, correct? It is not available. The only this nitrogen is a donor atom here. There's no other possibility. That's why nitrogen only attacks onto this, and after that Ag plus goes out. That's why we get RNC, and here we cannot write that we'll get RCN. This is not at all true because this site is not at all available, right? So reason of formation of isocyanide is AgCN, which is covalent. Cyanide, we have NaCN or KCN, which are ionic in nature. The mechanism of reaction is SN2.
Okay, sir. Sir, 2 minutes to be precise.
Write it down. It's important. Exam they have asked many times this. Write down the reason properly. Done.
Last point, sir. 1 minute.
Are you writing a book?
Yeah, no, sir. I'll say I write detailedly, sir, and yeah, that's why, sir.
Done, sir.
Carbon not available for bonding at all. Therefore, no possibility. How do I try to write as fast as possible, sir? Of or CN
Everyone has
atom.
done.
I also done, sir.
Okay.
Hey guys,
Now,
write slowly.
see, similar kind of reaction. We have same logic. We have in this reaction also. I'll show you. Second reaction. Reaction with KNO2 or NaNO2. Same, these are ionic compounds. Ionic compounds. So NO2 minus exists as this, N double bond O. And here we have the negative sign. And this is the donor atom, actually, oxygen. K plus and NO2 minus is this. So donor atom is what? Donor atom is
Atom which
oxygen.
donates.
Okay,
Oxygen.
Nitrogen can also donate since it is lesser electronegative than oxygen, but oxygen has excessive electron, right? One negative charge also on it. So that's why this gives you the major product. So the
That's
reaction.
Bhandar, sir. You can happily give.
What?
It has treasure. Bhandar of electron that you can give.
Yes. So when this reacts with what do you say? I do not know.
Okay, sir.
Plus it gives a Cl minus which can form actually NaCl. Okay. So this is, we call it as nitrite. Okay, it is nitrite. Oxygen is a donor atom. If nitrogen donates, that will be the minor into this. We don't write actually. Okay, but the reaction, same reaction with AgNO2. AgNO2 is what?
Silver nitrite.
AgNO2 is covalent.
Oh yeah, like that, yes, sir.
Right? So this gives you, suppose we have RCl with AgNO2, it gives RNO2 plus AgCl. It is nitroalkane. All these reactions are SN2. Okay.
So 1 second, sir. Yeah, guys, write slowly. Almost done, sir. Almost. Oh, okay. You won't change course. Okay, chill now. Done, sir.
I'll just write down the reaction this way. Okay. So in all these reactions, 1 degree alkyl halide we have. So it follows what?
SN1,
Again,
SN2.
right? So first one is aqueous KOH. Then we take CS3 ONA with CS3OH. SH minus RO minus Na plus CH3 minus Li plus LiAlH4. It produces hydride ion H minus. Okay, it's a very strong reducing agent. Strong reducing agent.
Done, sir.
Done.
Yes, sir.
What is the product we get in the first reaction?
Alkene.
We get ROH.
Oh, yeah.
Alkene is possible in elimination reaction.
Yes, sir. Yes, sir.
See what happens. This K plus takes this Cl minus, forms R plus. It's not like two-step reaction, but this has a tendency to take this. And since aqueous KOH we have, so water molecule behaves as a nucleophile that will attack from the backside. Okay, that ROH2 bond is about to form and this bond is about to break, and eventually H plus goes out from that. Okay, we'll get ROH. Similarly, here the nucleophile is CS3O minus. CS3O minus Na plus. The nucleophile is this, so the product is R.
OCH3.
It is an ether. SH minus nucleophile. SH minus, don't get confused. You can consider this as OH minus only. Product is thiol.
RSH.
RSH. What is the nucleophile here?
RO minus.
So product is ROR.
ROR.
Nucleophile is CS3 minus. Product is RCS3. Nucleophile is H minus. The product is RH, which is an alkyl.
Yes, sir.
Okay. Done? All of you?
Done, sir.
Okay. Now the next reaction is the reaction of, suppose I am taking RCl with silver oxide, Ag2O. Ag2O. This is dry. Dry means what?
Not water.
Moist means what?
It is nice. It like after putting Vaseline like that.
So when you have dry Ag2O, it forms ether.
Yeah.
If you have moist Ag2O, it forms alcohol.
Why, sir?
The mechanism is SN2,
Okay, sir.
right? Why it happens, you see, if you have Ag2O dry, right, means there is no water, so like OH is not possible to come, right? But I'll show you the mechanism how it goes. Ag2O is this plus RCl. The mechanism is SN2, and this lone pair attacks onto this. Why this attack is possible? Because this is
Partial positive character.
so it forms Ag. It forms Ag, OAG, R, positive charge here, and Cl minus goes out. Okay. Then what happens? This Ag plus comes out to stabilize this positive charge on this, and this Ag plus combines with Cl gives what? AgCl. Correct. Now this again behaves as a nucleophile for the other molecule. We actually take two molecules of alkyl halide for this reaction. So this one AgOR again attacks onto this alkyl halide. Mechanism is again SN2. This lone pair comes over here. This goes out. So it forms what? And finally from this Ag plus comes out and we'll get ROR plus Ag plus combines with Cl minus forms AgCl. So you get 2 moles of AgCl and 1 moles of ROR. Okay.
So 1 second, sir.
No second.
Wait, buddy, sir, please. I'm writing.
Ag2O moist. I'll just finish this. Moist means water is present, right? So what happens is Ag2O combines with water and forms 2 molecules of AgOH. Okay? So this gives the nucleophile OH minus. So easy a reaction, you see. RCl plus 2 OH minus we have here, or OH minus, simply I'll write down. OH minus gives you what? ROH plus Cl minus. So we get an alcohol with moist silver oxide. Dry silver oxide gives you an ether. All these are SN2, you must remember. No formation of carbocation, and hence no rearrangement.
One second, sir.
No second.
It's too much to write, sir. What to do? Sad. Yeah. Moist Ag2O, sir. 1 second.
Venkat, mute your video, bro.
Oh, sorry. Done, sir.
Wait. Yes. Huh. The all the reactions are SN2. Even if you see the two reactions I have given you, that one, halide exchange reaction. Okay, Schwartz reaction and Finkelstein reaction, right?
Yes, sir.
Those reactions are also SN2. Schwartz and Finkelstein, write down there. Those reactions are also SN2. Write it down there.
So in Schwartz, is there any logic for which halogens can be exchanged? Is it like more reactive, less reactive, or something like that, or any two random halogens?
The fluoride we are not taking in the Finkelstein because carbon-fluorine bond is very strong. So we cannot replace fluorine from that compound, from fluoride.
Okay, so bromine, iodine or something?
Huh?
Bromine, iodine or something?
We can replace bromine. That's what you see. RX is fluorine or bromine there.
Mm-hmm.
Okay?
Yes, sir.
With the salt of acid, RC double bond O minus Ag plus, with suppose alkyl halide R1Cl, if it reacts with this the salt of acid, RC double bond O minus Ag plus, again this RCO minus behaves as a nucleophile. The mechanism is SN2 and will end up getting an ester. Is it correct?
One sec, sir. Yeah, yes, sir. Yes, sir. I think it's right.
This O minus will attack where?
To R1, R1.
R1, right? So this O should attack with R1, no?
Oh, okay. That way you're asking. Okay. I thought that's
Or
the same thing only.
Not same thing. This kind of question they ask.
Oh, sorry.
Plus AgCl, correct?
Yes, sir.
Okay. There are reactions with NH3 derivative also. Ammonia derivative. For example, suppose we have RCl with NH3 or RNH2 amine, RNHR secondary amine, or RNRR tertiary amine. Okay, the product here is what? Right? This lone pair will attack onto this carbon, Cl minus goes out. So we'll get what? I'll just explain this here. When this lone pair attacks, you'll get this RNH3 positive charge on it, and this Cl minus goes out, right? Now to stabilize this positive charge, one H plus comes out, leaving this bond pair of electron behind. So it forms RNH2 plus HCl, correct? Yes.
Yes, sir.
Similarly, what we get here?
RNHR.
RNHR, right? So first
Yes,
is
sir.
primary amine. This is secondary amine. And this one is what?
3-degree amine.
And here what happens? Last one?
Bad. Oh, full on R only, sir.
No reaction.
Oh.
Did you understand all these 3-4 reactions? It's clear?
Yes, sir. But 1 second, sir, please. As usual.
Finish.
Yes, sir.
Okay. The next reaction is an important one. That is Williamson's ether synthesis. This reaction is reaction of alkyl halide with ethoxide ion. Any alkyl group we can take, like RO minus Na plus. Methoxy, ethoxy, anything you can take. The product here we get is ROR dash, this R dash I'll write down here, plus NaCl. This is the overall reaction. Formation of ether. Right? Mechanism is SN2. So this alkyl halide is preferred as what? 1 degree. Like for example, what is the product we get here? CS3O minus Na plus CS3Cl, and we heat this. The product is dimethyl ether. Even if you take this molecule, O minus Na plus CS3Cl, what is the product? This is the product we get. Or if you take this, Na plus Cl here, what is the product we get here? Tell me.
CH3O, that Trishul.
What? This Trishul and this Trishul.
Yes, sir. Yeah, yes, sir.
So CS3O minus with this Trishul, right?
Yes, sir. Why, sir? Of course it had to happen.
Alkyl halide is 3 degree.
Okay.
Favors SN1.
Oh, yeah.
Right. So for the better yield,
Venkat,
alkyl
I
halide
can't hear sir properly, bro. Can you mute?
must be what? Must be 1 degree. Right. So better yield, the alkyl halide must be. See, actually, what happens when this OCH3 minus tends to behave as a nucleophile? So this has tendency to attack from the back, right? Then this will go out. This nucleophile can't attack from this side because इसको तो बचाना है ना बाहर living group को. To make this living group go out, like goes out, if it is possible, this thing is possible only when the nucleophile attack from the back side. ये पीछे से आके इसको push करेगा उधर. Got it?
No, sir. How? What?
Huh?
I didn't get that backside and all.
This attack will be from the back side so that this can go out easily. इधर से ये attack करेगा तो ये कैसे निकलेगा?
Oh, yeah.
पीछे से आके धक्का देगा इसको तो दिल go out.
Yes, sir.
So that's why in SN2 always backside attack होता है. Always we have backside attack so that the leaving group can go out easily. Means preferred है ये. Like you can do this. Okay, this will attack from this side, but again the reaction won't do that because this side it will be difficult for this leaving group to go out because it starts interacting with the nucleophile also. Right, there will be some hindrance and all. But here also backside attack is not possible because this carbon is slightly positive charge, right? And this is surrounded by the 3-methyl group. So here we have the steric crowding. So this won't facilitate the attack of nucleophile onto this carbon atom, the steric crowding. That's why the reaction is not possible. Yes. No.
Okay, sir. But we'll write theory, sir. Wait, Marty, please.
What about others? Did you understand this? CLR. Correct. Okay. So what we can conclude this, for the better yield of product ether in Williamson ether synthesis, the alkyl halide must be primary, right? A smaller alkyl group will go with the halide part. Okay. So suppose if I have to obtain this as a product in Williamson ether synthesis, this as a product in Williamson ether synthesis, what should be the nucleophile for this product and what should be the alkyl halide for this product, so that this reaction gives you this product.
PCL. CH3. H.
Tell me.
One sec, sir.
BH3H.
What? What should be the alkyl halide? Sorry, what? Venkat, you mute yourself. Yes, tell me.
Methyl chloride or methyl halide.
Methyl chloride. Okay. So you said the alkyl halide should be this CS3X, and the nucleophile is what?
Okay.
This ring, right? O minus Na plus. Something like this. Yes, this is
I don't
correct.
feel that, sir.
Huh?
Is that
See, you cannot take the halide and with a larger group, because again, if you have large group here, then the attack of nucleophile is difficult,
okay, sir?
right? Ring structure hinders the attack of nucleophile onto that carbon atom. That's why you always keep this in mind, that we always have a smaller alkyl group with the halide ion in Williamson ether synthesis for the better yield. They ask this question, which is the best combination for the product in Williamson ether synthesis? Okay, two things you have to memorize. The product of this reaction is an ether, right? It involves, the mechanism is SN2, and when it is SN2, there is no carbocation formation, no rearrangement, nothing is there. Just you have to take the R group of RX, and that you have to attach with the nucleophile, whatever it is given in the given in the question. Understood this?
Yes, sir.
Okay. So this is it. SN2 reaction for alkyl halide is done. Alkyl halide also shows elimination reactions. Okay, there are some elimination reactions also possible, like we have reduction, a dehydrohalogenation reaction, right? Removal of HX is an elimination reaction. Okay, action of heat also, HX removes, right? HX goes out, hydrogen halide, that is also an elimination reaction. So both of these reactions leads to the formation of alkene. Okay, so elimination reactions leads to the formation of alkene. There are few SN1 reaction also possible, and SN1 reaction possible always in polar protic medium. Polar protic medium means you have hydrogen attached with an electronegative atom in the solvent, like H2O. H2O is a polar protic solvent. Okay, oxygen hydrogen bond is there. Okay, you have this one. Any other example, like we have NH3, a polar protic solvent, ammonia. Okay, we can also have another examples. What we can say, polar protic solvent H2O. We can have alcohol, ROH, again hydrogen attached with O, right? Polar protic solvent.
NO2. NO2.
NO2 is not polar protic. Where is hydrogen into that?
Oh yeah.
Polar protic solvents are those solvents in which hydrogen is attached with the electronegative element. Okay, and polar protic solvents favors SN1 reaction. Why it favors SN1 reaction? For that thing, you have to see the video. You have to watch the video for that. Okay. So
Okay, sir.
polar protic solvent SN1, polar aprotic solvent SN2. Okay. CCl4 is a polar aprotic solvent. Ether, polar aprotic solvent. There is no oxygen hydrogen bond. There is no hydrogen and electronegativity bond, electronegative element bond. So all those solvents in which hydrogen and electronegative element bond is not present are called polar aprotic solvent. Okay, so I'll share the video of reaction mechanism. Just go through it once whenever you get time. Next class we'll start with few 2-3 reactions. We have SN1, then we'll see some elimination reaction. There are few more reactions which we have already done in hydrocarbon chapter. We'll just go through it, and then we'll start aryl halide. We'll finish that also next class. Understood?
Okay, sir.
On the Learnist platform, assignment is given for this. Okay, you just go through, do whatever you can. However, the chapter is not finished, but you can try 10, 15, 20 questions. Just give it a try. Okay.
Okay, sir.
Any doubt?
Yeah.
Okay. Chalo. Thank you. Bye bye.
Thank you, sir.
Thanks, sir. Bye, sir.
Thank you.
Bye.
Thank you, sir. Bye.
Thank you. Bye bye.